Now let's look this program, review this specific example in Mars. I have it's open, and this is my frame store code, and I told you I'll show you how to add the restore code. Okay, so let's say I don't have that restore code with me. Okay, I'm writing the restore code. So what I all need is to copy from line 40 to 44 in this case, because my first stored word is appearing in line 40. So I copy it and I save it here. So what I'll do, I'll just change it to load word, load word, load word, load word, and here I change it to stack pointer. Okay, and that become my restore code, and I call back from here, right? So this is my function, and in this case what I've done, I have made that function main, okay, which is like nothing but a label main. My main program is one part, like very beginning it started, and then I have the self-contained factorial code, right? So a function, you can spot it with an start with a label and end with a JR. Okay, end with a JR, and somewhat the restore code, like it's at least it should have this guy, okay, and this guy, because our convention is that we always store FPRA, no matter if it is needed or not, doesn't matter, just store it and have your adjusted your SP. So this is your restore code at minimum and a jump register. That's the end of your function implementation on the assembly language on the low level. Okay, so it is nothing like a high level function implementation, right? The function implementation has is start with a label, RT storing code, body, then RT restore code and return, and usually it has a specific label, that part of code where we restored the frame and jump back to the caller, we label it as an that function name underscore RET, just on convention again, right? And it's a suggestion to you to follow this convention, because it will help a lot to kind of formalize your writing of the function code in the assembly, and also it will help you in debugging. Okay, and inside the body you can do whatever implementation you want to do. Okay, so bottom line starts with a label, a function, runtime, user runtime environment, storing code, body, and restore and call, like jump to the caller. This is what the function is. We assemble it. Okay, let's see first. Let's see how it runs. Let's take an example, the same example 5, and factorial is 120. Now let's look at the step by step. Okay, so where we are calling, let's see, we reset everything and we are calling here. Okay, this is my call from the main, and let's do another. Okay, so this is my start of the function, which we can go from here, factorial here. So if we kind of double click, it brings you to that place. So let's take a stop here. Let's also take a stop here, that is a recursive call to the factorial, and let's take a stop here. Okay, so we run it, same example 5. Okay, now it stops from the very first main body point where I'm calling factorial for the first time. And let's look at that stack data. So you can do it by current stack pointer. Okay, see everything is 0 in the stack pointer, starting from FFE0. So at this point, look at the program counter, like it is 2020 and if you go and execute it, okay, it jumps into the address which is for the label fact 078, right? And look at the PC is now it's that address, and also look at the return address. JL caused the return address to be 0024, which is the very next address of the first JL call. Our first JL call was at this, so next instruction that move S1 V0 to S1 was at 024, right? This address 400024, that is being stored as an array. Okay. Now what we do, we keep on changing the, like, making the frame for storing your runtime environment. So we change the stack pointer. Okay, move the stack pointer first, and then store frame pointer value, which is like current value is 0. So you won't see any change, but yeah, this is being saved here. And then we save the value of the array, which is 024, it's stored here, and then A0 as 5, S0 as 5, and then we go to the body, right? Body of this. So let's continue, and it ultimately go at a point where we are calling itself, right? Which is V0 as A0 as 4, right? You look at the A0 value. A0 is, where is the A0? Oh, here is 4, right? A0 is 4. So this is your frame, like 4 value frame, and your stack pointer is pointing somewhere here, right? Which is like FE8, yeah, this point. So you have 2 word boundaries so that you can push a double word if needed. So at this point, I do one step. Now see, array changed because it is calling itself. It's changed to 400A8. Why? Because this one is A4 and next instruction is A8. So this JL causing the return address value to be stored as A8. So if it is done with this call, this instance of this function call, it should come back to this line 53, which is address is 4000A8, right? So that's why array become this, and your control is coming at the store frame point, frame storing, RT storing. So we change the stack pointer first. So stack pointer is somewhat moved to somewhere here, maybe 1, 2, 3, 4. Yeah, maybe here, and from here basically 18, something like FFF0 EFD4. Okay, so it goes there. Yeah, D4, maybe here. Yeah, I think this is here. Anyway, so that's not important. Important is, let's see how it stores. The frame pointer is stored here. Okay, so because the frame pointer is now FFFEFFC, it was the frame pointer of this first frame. And then step 2 is your store the return address, and then value, and then your stack the 5, right? The 5 value. So why it is dynamically changing? Because it's basically showing you with respect to the current stack pointer, right? Current stack pointer. So that's why this kind of becoming a dynamic. Okay, so what can we do to prevent this? Can I do, or we can actually see this frame like this. Your stack pointer was here basically. Okay, anyway, let's continue. So now we continue, we come to the next instance of the JL. We go there, array changes. Array doesn't change, it is the same instance of, like, same places it need to return back, but we are changing the frame stack pointer again, and then storing the values. Okay, now is 3, 4, and then we go and another instance of call. We keep on saving things on the stack. Okay, and then my A0 is 1 now at this point, so another frame. Okay, another frame is stored, and then go another. Okay, now it is your base case, right? So we take the frame A0 and A01, and then from here, now it should hit your base case, right? Yeah, it's basically 1. Now you see the V0 is set to 1. Okay, and then it goes into your restore code, right? So it's restoring back array S0, A0, and restoring back your stack pointer. Okay, and jump to the caller, right? So it was called by itself, so it will go back here, right, at line 53. Let's see it. See, it's go back to the line 53 because that's the part this instance of the function call was made. So it goes into 53 and continue on that. Now it comes to the end part, factorial return. So it's restored the frame, stack pointer is changed and coming back to itself, second phase. So look at this storing of V0, right? V0 is changed to 2, rest frame is restored, and then come back to 6, right? And then it becomes 18, 18, and then restore back 7, 8. And now at this point, it returned back. Let's now at this point, see your RA become 0024, which is basically trying to return back to the call. This is where end of the whole execution of the recursive factorial function call. And at that point, my RA, by restoring frame and everything, I came back to a point where it will jump to my main code where I called the function in the very first place, which is at JL, one more stop. Yeah, here 004000024. That's what your return address is at this point. So that's how you go back to the main program, and then we do the rest of the things like printing the factorial, printing the result, and so on and so forth. Your V0 was returned with this value 120. So this is how your factorial programs work, or recursive call works, and this is what we mean by a function implementation at the very low level. Also, one fact you see, look at these stacks, no value has been destroyed. Though we pop out the frame, and pop out the frame really doesn't mean it wipe out the memory. The value is still there, only that stack pointer moved so that new push and new frame creation will override this. Okay, so this part you need to understand very carefully, that in the hardware nothing is destroyed. Okay, unless you purposefully like wipe it out, make it to 0 before you return, then you'll go to the initial state of 0. But usually your high level program doesn't do it because it then will incur more runtime. Right? You are writing into the memory, wiping on the memory, unless it is a very crucial security issue, no one that does it. Okay, your data is still there. It's only that those part of the memory is now overridable. Okay, if it was in an active frame, it was not supposed to be overridable unless there is a bug in your program, and it should stay as long as your function is active. Okay, your instance of the function call is active. So that's come to our end of this lecture. procedure and function implementation. If you have further question, please let me know over email or ask me in the class.